Okay, so we have gone through some basics of differential amplifiers in the previous sessions, and we have seen a typical symbol used to represent this operational amplifier. So we have seen the pin number 2 and pin number 3 of these ICs are nothing but the inverting input terminal and non-inverting input terminal. What do you mean by inverting input terminal? Whenever we provide a sinusoidal signal to this input, that is pin number 2, the output which we are getting at pin number 6 will be 180-degree out of phase. And this is the reason why this input terminal is known as inverting input, right? And whenever we are providing the input signal to pin number 3 with respect to ground, at that time the output which we are getting at pin number 6 will be in phase with the input signal. Okay, so there will not be any phase shift between the input and output signal. That is what we have seen. And this pin number 4 and pin number 7 are nothing but the positive and negative power supply to be provided to the operational amplifier. Okay. So now what happens in this particular triangle? Okay, what are the different stages our input signal will go through, and finally we are getting output at this terminal, right? So what are the different stages and what happens in these particular stages? That is what we need to see. So we'll try to understand the block diagram representation of operational amplifier. As we have discussed in the previous sessions, that the operational amplifier will go through total 4 different stages, right? So the first stage is known as input stage. So this is my first stage where we are providing 2 inputs. Okay, input 1 and input 2. One input may be inverting, another input may be non-inverting. Okay, so this is our first stage, right? So this input stage requires very high input impedance. Why? To avoid the loading on the sources. Okay, and it has these 2 input terminals. It also requires the low output impedances. That is what we have seen. Okay, so all these requirements, as we know, are achieved by dual input balanced output differential amplifier. Okay, so this dual input balanced output differential amplifier will behave as an input stage of the operational amplifier. Okay, and what is the function of this differential amplifier? It will amplify the difference between the 2 input signals. Okay, what is the difference? Difference Vd is nothing but V1 minus V2. So whatever this difference signal is there, difference voltage is there, that will be amplified, and we will be available with some output voltage signal at the end of this input stage. Okay, so this differential amplifier has high input impedance. Okay, and this stage will provide most of the voltage gain of the amplifier. Okay, so now this is my dual input balanced output. Okay, so we will be available with the output voltage at the end of this input stage. Okay, and this output voltage is further provided to one more stage which is known as intermediate stage. Okay, so here we will get the second stage of operational amplifier, which is intermediate stage. Okay, so the output of input stage drives the next stage, which is an intermediate stage. Okay, this is another differential amplifier, but this time this is dual input unbalanced output. Okay, or you can say single ended output. Okay, so here we will get only one output like this. Okay, so this is what we will get in this particular case, right? So the overall gain requirement of the op-amp, as we know, is very much high. Okay, so the input stage alone cannot provide such a high gain, and this is why we are provided this intermediate stage. Okay, so the main function of the intermediate stage is to provide an additional voltage gain which is required. Okay, so some of the voltage gain is provided by this input stage, and another additional required voltage gain will be provided by this dual input unbalanced output differential amplifier. Okay, so practically talking, this intermediate stage is not a single amplifier, but it is the chain of cascaded amplifiers, which is also known as multi-stage amplifiers. Okay, so according to our required gain, we will be using these multi-stage amplifiers. Okay, and the output of this intermediate stage is now provided to another stage which is known as level shifting stage, and that is my third stage, which is known as buffer stage as well as level shifting stage. Okay, buffer and level shifting stage. Okay, so as we know, all the stages are directly coupled to each other. Okay, as the operational amplifier amplifies DC signal also, the coupling capacitors are not used to cascade the stages. Hence, what will happen? The DC operating point voltage level of previous stage will get applied as the input to the next stage, right? Hence, wait a minute.
Party hours. પછી કરશે ચાલશે.
Okay, so we were talking about this level shifting stage, right? So whenever we talk about the DC quiescent voltage level, that will be applied as the input to the next stage. Hence, stage by stage DC level increases well above the ground potential, and such a high DC voltage level may drive the transistor into saturation. Okay, so this further may cause some distortion in the output due to clipping, and this may limit the maximum AC output voltage swing without any distortion. Hence, before the output stage, it is necessary to bring such a high DC voltage level to 0 volts with respect to ground. Okay, and what does this lever shifter stage brings? It brings the DC level down to the ground potential when no signal is applied at the input terminals. Then this signal is given to the last stage, which is the output stage. Okay, so basically, if we talk about this buffer stage, it is nothing but an emitter follower whose impedance is very much high, and it will prevent the loading of the high gain stage. Right. So the output of this buffer and level shifting stage will be provided to our final stage, which is nothing but the output stage. Okay. And finally, we will be available with some output over here, right? So the basic requirement of an output stage are what are? These are low output impedance, large AC output voltage swing, and high current sourcing and sinking capability. Okay, so what we are using? We are using the push-pull complementary amplifier, because this amplifier meets all the requirements which is required for the output stage of the operational amplifier, right? So this stage increases the output voltage swing and keeps the voltage swing symmetrical with respect to ground. Okay, the stage raises the current supplying capability of the operational amplifier. Okay, so this is what happens in this internal block. Whatever we can see over here in this triangle, these four stages are available: input stage, intermediate stage, buffer and level shifting stage, and finally the output stage, right? And we have also seen what happens. See, the input stage we will be available with some differential amplifier, right? A balanced input, dual input, balanced output differential amplifier. As an intermediate stage, we will have dual input, unbalanced output differential amplifier. In this buffer and level shifting, we will get the emitter follower circuit. And at the output stage, we will be having push-pull complementary amplifier. Okay? So this is our block diagram of operational amplifier. Right? After that, we have to understand what are the voltages and what are the currents that are associated with these operational amplifiers. Okay, it is not that only the input current and output current that are associated with the op amps amplifier, but apart from these, some parameters are there which you need to know. You need to know about the currents, and you need to know about the impedances. Okay, so practically talking, an input stage is nothing but the transistorized differential amplifier stage, which is using two transistors, right? And we know that the base terminal of these two transistors are the two input terminals of the operational amplifier. So what will happen? Some small DC base current is necessary to maintain the operating state of the transistors, and these two base currents are the input bias current of the op amp. Okay, so we have this term. Now we have input bias current. Okay, and the typical value of this DC input current is of the order of 500 nanoampere or less than that. Okay, now talking about the impedances. Okay, so the input impedance Z in, right? We know the value of Z in. It should be very much high. Okay, what is the high value? Typically 1 mega ohm or even greater. Okay, so to increase this input impedance, what we can use is the field effect transistors instead of bipolar junction transistor. Okay, so in such a case, what will happen? The gates of two field effect transistors will act as the input terminals of the op amp. Okay, and then at the output stage, what is the output stage? We have some emitter follower, and we know that emitter follower are having very low output impedances. Okay, so if we talk about the output impedance Z0, it should be very much low. Ideally speaking, it should be equal to 0. Okay, so typical value of output impedance in case of operational amplifier is 75 ampere. and the maximum output current, the maximum output current is around 25 milliampere. So these are the typical values of currents and impedances which are associated with operational amplifier. Okay. Now, what are the voltage levels? Or you need to understand one term which is saturating property of op-amp. Now, why this is important? See, we know that whenever an input is provided to the operational amplifier, what will happen? According to the value of gain provided by this amplifier, my input signal will get amplified to a different value, okay, which is very much high compared to the input signal. Okay, so suppose I have an input signal of 1 millivolt, and if my gain provided by the amplifier is 500, then output voltage will be equal to 500 millivolt. Okay, then suppose my input signal is 1 volt and the gain is 500, then in that case the output voltage will be very much high. See, it is 500 volt. Okay, so practically there must be some limit, because ultimately we are limited by the supply voltage provided to the operational amplifier. Okay, and we know typical values of DC supply voltage will roam around some 4 volt to 15 volt or 20 volt max. Okay, so if my supply voltage is 20 volt, 15 volt, then how this voltage is increases to 500 volt? According to, and theoretically it is true, if we are providing the gain of 500 and if my input signal is 1 volt, then definitely 500 voltage will be there. But that does not happen actually with the operational amplifier. Okay, so whenever the output voltage reaches the supply voltage, after that, irrespective of the input signal, the output voltage will fluctuate between the saturation limits of the op-amp. Okay, so this supply voltages of op-amp, what is that supply voltages? Supply voltages we know is plus VCC and minus VEE. Okay, so this level, this supply voltage level will decide the maximum output voltage of the operational amplifier. Okay, and practically the op-amp output will saturate at the voltage slightly less than the supply voltages plus VCC and minus VE. Thus, the output voltage of the op-amp can be driven to within 1 volt of plus VCC and minus VE before the output saturation takes place. And this is called saturating property of operational amplifier. Okay. So if we talk about the maximum output swing of the op-amp, it will be 90% of the supply voltage, or you can say 0.9 times the supply voltage. Okay, so suppose my supply voltage, I am using the supply voltage of plus or minus 15 volt, then the maximum output voltage swing, maximum output voltage swing will be 0.9 times plus or minus 15 volt, that is plus or minus 13.5 volt. Okay, so this will be the maximum amount of output voltage which we will be able to get in this particular case, right? So ideally it is considered that the output voltage of the operational amplifier saturates at plus VCC and minus VEE level. Okay, so if we talk about the output voltage now, I'm talking about the output voltage, right? This is my 0 DC level. Okay, and this is our input signal. Okay, the magnitude may be any. Okay, so the output will saturate between these limits, ideally plus VCC and minus VEE. Okay. So these are my ideal saturation levels, that is plus VCC and negative VEE. Okay. So this is the output levels with 0 DC level. Okay. So this is all about the voltage level as well as saturating property of the operational amplifier. Right? Now let us try to understand the characteristics of this operational amplifier. Okay. So let us talk about the ideal op-amp characteristics first, and then we will move on to practical op-amp characteristics. You must know the characteristics, and as we know, we already have discussed certain characteristics. Say if we talk about the input stage, then we must know that the input impedance provided by the input stage must be very much high. Similarly, if we talk about the output impedance, it must be very much low. Okay, so these are the this is nothing but the characteristics of this operational amplifier. Okay, so what are the characteristics that are offered by amplifier, and what are its values, what are the ideal values of these characteristics? First we will go through the ideal values, and then we will move on to the practical values of op-amp. Right, so we have this operational amplifier. Okay, this is nothing but a symbolic representation of op-amp, right, where we have two input signals V1 and V2, and we are getting output voltage V0 at the pin number 6. Okay. These are my supply voltages plus VCC and minus VEE. Okay. Let V2 be at inverting terminal and V1 be at non-inverting terminal. Okay. So ideally, whenever these two inputs are provided, V1 and V2, what is the signal that gets amplified? The signal that gets amplified is nothing but the difference between these two inputs. Okay, this difference voltage VD will get amplified as per the values of gain provided by this amplifier, right? So now at input signal V1 there must be a flow of current I1, and at input terminal 2 there must be another current flowing. Okay, so ideally what should be these values? See, right now I have not provided any voltage to these two terminals. Okay, so if we talk about the difference voltage, then difference voltage should be equal to 0. Okay, and as difference voltage is 0, the input current I1 must also be equal to 0, and I2 must also be equal to 0, right? And whatever output we are getting, that output will be equal to 0 as of now. Okay, and when this is the amplification stage, okay, what should be the amplified voltage? We will require the maximum amplification which is possible. So ideally speaking, if we talk about the gain, open loop gain of this amplifier, that must be equal to infinite. Okay, then and then we will get the maximum output voltage. Okay, so this is nothing but the ideal operational amplifier, right? So now let us take one by one characteristics of this ideal operational amplifier. Okay, so first of all, using this ideal op-amp, we need to consider some things. Okay, the first thing is an ideal operational amplifier will draw no current at both the input terminals. Okay, as you can see, I1 equal to 0 and I2 equal to 0. And this is the reason why you can say its input impedance is infinite. Okay, so we can say now Zin is equal to infinite. Then and then you will make sure that I1 and I2 are equal to 0. Okay, so any source can drive it and there is no loading on the driver stage. Second, the gain of an ideal amplifier is equal to infinite. So what will happen? The difference input Vd, which is nothing but the difference of V1 minus V1 and V2, that is V1 minus V2. Okay, so that difference Vd is essentially zero for the finite output voltage V0. Okay, and third, the output voltage V0 is independent of the current drawn from the output terminals, and thus its output impedance, if we talk about ZO, will be equal to 0, and hence output can drive infinite numbers of other circuits, right? So these properties are expressed generally as the characteristics of the ideal amplifier. Okay, so the various characteristics of ideal operational amplifier are: number one, infinite voltage gain. Infinite voltage gain. Okay, AOL is infinity. Okay, so infinite voltage gain of operational amplifier is denoted as AOL. It is nothing but the differential loop gain, and it is infinite for ideal op-amp. The second characteristic is infinite input impedance. Infinite input impedance, that is R in or Z in, and that is equal to infinite. Okay, so the input impedance, it is denoted by R in, and its value is infinite for ideal op-amp. Okay, and this will ensure that no current can flow into an ideal operational amplifier. Then talking about the output impedance, then we should have zero output impedance. So R0 equal to 0. Okay. And what it will ensure? The zero output impedance will ensure that the output voltage of the op-amp remains same irrespective of the value of the load resistance connect. Okay. And this is the required. Okay. Then we have another characteristics which is about the offset voltage. Okay, so offset voltage of the ideal op-amp is 0. Now what do you mean by this offset voltage? Let us try to understand this term. Okay, it is denoted by VIOS and its value is typically 0. Okay. So you know that the presence of small output voltage will always be there, though the input voltage V1 and V2 are equal to 0, and this is called offset voltage. If you do not provide any amount of voltage at the two input terminals of the op-amp, still we will get a very small output voltage at the end of the op-amp, and this output voltage is known as offset voltage. Okay, so for ideal operational amplifier, the value of offset voltage will be equal to 0, and it will ensure zero output for zero input signal voltage. Okay. Then the fifth characteristics of ideal op-amp is infinite bandwidth. Okay, now bandwidth, we know. What do you mean by bandwidth? It is the range of frequency over which the amplifier performance is satisfactory. Okay, whenever we talk about the bandwidth, it indicates the maximum and minimum values of the frequency. Okay, so in between this frequency, whenever we are operating our operational amplifier, it will give us the satisfactory performance. Okay, the true output will be provided by the that. Okay, and if we have another frequency which do not provide us the satisfactory output, then this is out of range of this bandwidth. Okay, so the bandwidth of an ideal operational amplifier is infinite. This means that the operating range is from 0 hertz to infinity. Okay, this will ensure the gain of the op-amp will be constant over the frequency range from DC frequency, that is 0 frequency to infinite frequency. Okay, what does it mean? It means that operational amplifier can amplify DC as well as AC signals. Okay, so bandwidth BW for an ideal operational amplifier will be equal to infinite. Then if we talk about the common mode rejection ratio, that is CMRR, so the value of CMRR should be as high as possible. That is what we have seen. Okay, so for ideal operational amplifier, the value of CMRR is equal to infinite. Okay, so talking about CMRR, it is nothing but the ratio of differential gain and common mode gain. Okay, rho is equal to AD upon AC. That is what we have seen. Okay, so the infinite CMRR of an ideal op-amp will ensure zero common mode gain, and due to this common mode noise output voltage is zero for ideal op-amp. Okay, we have seen that common mode voltage is available, which is nothing but the average of two input signals V1 plus V2 by 2. Okay, so that common mode voltage will affect the output of operational amplifier, and if we have very high value of CMRR, then we can almost neglect the effect of this common mode voltage. Okay, so ideally the value of CMRR should be equal to infinite. And then if we talk about the slew rate, the ideal value of slew rate is again infinite. Okay, so slew rate is generally defined by capital S, and its value should be equal to infinite. Okay, so what this infinite slew rate ensures? It ensures that the change in output voltage occurs simultaneously with the change in input voltage. Okay, if I suddenly change my input, then what should happen? Output voltage should change instantaneously. Okay, and that depends on this value of slew rate, because the slew rate is very much important parameter. Okay, when we apply input voltage, okay, suppose it is a step type, okay, it will change instantaneously, then the output also must change rapidly as input changes. Okay, so if output does not change with the same rate as the input, then there occurs the distortion in output. Okay, and such a distortion definitely is not desirable. Okay, so when we have infinite slew rate, it indicates that the output changes simultaneously with the changes in the input voltage. Okay, so this parameter slew rate is actually defined as the maximum rate of change of output voltage with time. Okay, so if we talk about slew rate as, it is the maximum rate of change of output voltage with time. Okay, and it is generally expressed in volt per microsecond. Okay, so the ideal value for this slew rate will be equal to infinite. Then there is one more characteristics of ideal op-amp, which is the temperature has no effect. Okay? No effect of temperature. Okay. So if we increase or decrease the value of temperature, then the output will not be affected by the raise, increase or decrease in the temperature. Then we have the power supply rejection ratio. Okay, so ideal value of this power supply rejection ratio is 0. Okay, this is also known as PSRR, power supply rejection ratio, PSRR, and that should be equal to 0. Okay, now what do you mean by this PSRR? See, the power supply rejection ratio is defined as the ratio of the change in input offset voltage due to the change in supply voltage which is producing it. Okay, and we need to keep other power supply voltage constant. Okay, so you can also call it power supply sensitivity. Okay, this power supply rejection ratio may also be known as power supply sensitivity. Okay, so now if we talk about the operational amplifier, then we know that we are available with two power supplies. One is plus VCC and another one is VEE. So suppose I am keeping this VEE constant. Okay, if I am considering VEE constant. Okay, and due to change in VCC, suppose there is the change in input offset voltage. There is change in input offset voltage, then PSRR, power supply rejection ratio, is defined as delta VIOS by delta VCC by keeping another power supply constant, that is VEE in this case will be constant. Okay, so this is nothing but the ratio of the change in input offset voltage due to change in the supply voltage. Okay, any one supply voltage, whenever I am changing VCC, I am observing there is a small change in the input offset voltage. Okay, so when I take the ratio of these two quantities by keeping VE under supply voltage constant, I will get the value of power supply rejection ratio, and that should be ideally equal to 0. Okay, and practically it should be minimum. Okay, now suppose I have VCC fixed. Okay, so for a fixed VCC, okay, if there is change in VE, okay, which cause change in input offset voltage, then power supply rejection ratio PSRR is ratio of change in input offset voltage to the change in supply voltage by keeping another supply voltage constant. Okay, so generally these are expressed as millivolt per volt or microvolt per volt. Okay, and ideal value, as we have seen, it is equal to 0. Okay, so these are the characteristics, ideal characteristics of the op amp. Okay, if we talk about the open loop voltage gain, okay, let us summarize. If we talk about the open loop voltage gain AOL, that should be equal to infinity. If we talk about the input impedance Rin, it should be equal to infinity. If we talk about output impedance R0, that should be equal to 0. If we talk about the offset voltage VIOS, that should be equal to 0. If I talk about the bandwidth of op amp, ideally it should be equal to infinite. Okay, if I talk about the common mode rejection ratio, it should also be equal to infinite. If we talk about the slew rate, it should also be equal to infinite. And if I talk about PSRR, just we have seen that should be equal to 0. Okay, so this is nothing but the ideal characteristics of operational amplifiers, or we can call it op amp. Okay.
Excuse me, sir.
Yes, please.
Can PSRR written as efficiency?
No. It is not. Yes, you can also term it as an efficiency, because if we have increased value of PSRR, then it will affect the output voltage. Okay. So indirectly we can call it efficiency, but it is nothing but the rejection ratio of the operational amplifier basically, because we are available with two supply voltages, and if we increase or decrease the value of supply voltages, then what is going to happen? There must be a change, not must be, but that there should be a change in offset voltage. Okay. So the ratio of this change in offset voltage to the change in supply voltage will give us the value of PSRR. Okay, and ideally it should be equal to 0. 0 means when I change the supply voltage, the offset voltage is changing almost 0. Okay, and this is the ideal thing. This is the ideality of operational amplifier. Okay, so you can relate it with the efficiency, but it is not exactly efficiency, because definition of efficiency is somewhat different. We are relating efficiency with its output voltage only with respect to input. Okay, and this is related with the offset voltage. So PSRR ideally should be equal to 0. Now let us talk about the voltage transfer curve. See, we will be available with some input voltage V1 or V2, which is to be applied at inverting terminal and non-inverting of inverting terminal of the operational amplifier, and finally we will get some output voltage. Okay, so if we have the infinite gain, then as we know, output voltage is saturating between the two saturations level, plus VCC and minus VEE. Okay, so what should be the voltage transfer curve? Okay, so first we will consider ideal operational amplifier, and then we will move on to practical operational amplifier. Okay, so if we talk about this voltage transfer curve, okay, when I talk about voltage transfer curve, what is it? It is nothing but the graph of output voltage, graph of output voltage V0, which is plotted against the differential input voltage VD, against the differential input voltage VD. Okay, so let us try to understand this. See, graphically what we are providing, we are plotting the value of difference voltage VD against the output voltage V0. Okay. So this is my plus VD, negative VD, and output voltage in this particular case, right? So now consider the ideal voltage transfer curve first. Okay, I'm considering the ideal op amp. So ideally what we have open loop gain is equal to infinite. Okay, and what is this gain? This gain is nothing but the ratio of output voltage to the input voltage. What is input voltage? Input voltage is VD. Okay, so the value of this ratio V0 by VD is infinite, such that you can call VD is equal to V0 by infinite. Okay, and that should be equal to 0. Okay, so this is our ideality. The difference voltage VD will be equal to 0, then we will get the output voltage V0 is equal to infinite. Okay, so V0 in this case would be equal to A0L times VD. Okay, so now we know if we have infinite gain, then our output voltage must be infinite. But as we have already seen, the output voltage, infinite output voltage is not possible. Okay, so what should be the output voltage in this case? The maximum voltage of the op-amp, supply voltage of the op-amp. Okay, so we have two supply voltages, plus you can say saturation voltage in positive direction and saturation voltage in negative direction. Okay, so my voltage transfer curve would be something like this. Okay, from 0 it will increase to plus Vset, and then irrespective of the value of Vd it remains constant. Similarly, the case is with the negative direction. Okay, so for 0 input, the output of op amp is always at saturation level. As you can see, we have discussed this, right? So the level may be plus Vset or minus Vset. Why? Because of the infinite gain. Okay, so the voltage transfer curve for ideal op amp is nothing but a vertical line as shown in this particular figure. Okay, so the ideal range of input for linear operation of the op amp will be equal to 0 in case of ideal operational amplifier. Okay, but this is not true for the practical value. Okay, so now let us try to understand the practical voltage transfer curve, okay, with which we are actually dealing. Practical voltage transfer curve. Okay, now if we talk about practicality, then what will happen to the open loop gain? Now open loop gain will be some finite value. Okay, it is not infinite. Okay, so if we talk about one operational amplifier IC741, then value of gain is 2 into 10 raised to 5. Okay, that means whatever will be the input signal, the output will be 2 into 10 raised to 5 times the input signal. Okay, so in this case we have V0 is equal to AOL times VD. Okay, so what is AOL? AOL is 2 into 10 raised to 5 times VD. Okay, and output voltage will now saturate. So plus Vset will be equal to 2 into 10 raised to 5 times VD. Okay, and we know the saturation voltage. Saturation voltages are almost, what is the value? Saturation voltages are almost plus or minus 15 volt. Okay, so if we talk about difference voltage now, difference voltage is equal to plus or minus V saturation, that is 15 volt divided by gain 2 into 10 raised to 5, and that will give us the value plus or minus 75 microvolt. Okay, see, this is the range. If I go from 0 to 75 volt, sorry, microvolt, then after these values my output voltage will saturate. If I give negative supply voltage up to minus 75 microvolt, after if I further increase, my output is going to saturate. Okay, so practically till VD is between this minus 75 and plus 75 volt, output will vary linearly with the input. Okay, so talking about practicality, practically till VD is between minus 75 microvolt and plus 75 microvolt, the output will vary linearly with input. But once Vd will exceed this value, Vd exceeds plus or minus 70 microvolt, what will happen to output? Now the output will be saturated. The output is saturated. Okay. So talking about the voltage transfer curve, the practical voltage transfer curve is now this. Okay. So I'm taking difference voltage on horizontal axis and output voltage on vertical axis, right? So we have two limits. Okay, let us say this limit B, this is my point A, which indicates negative 75 microvolt, and this is my point B, which indicates positive 75 microvolt. Okay, so we have set one limit. We are available with this limit. Okay, within this limit, what will happen? The output, the voltage transfer curve will have linear value. Okay, so if I increase the input value from 0 to, say, let me set this saturation voltage plus V set, and this is negative V set. Okay, now what I am doing, I am increasing the voltage from 0 to 75 microvolt. Okay, this B point indicates plus 75 microvolt and A point indicates negative 75 microvolt. So when we increase voltage from 0 to 75, we will have a linear relationship like this. Okay, up to this instant. If I further increase voltage beyond this 75 microvolt, what is going to happen? My output is going to saturate like this. Okay, similar thing happens when I increase the voltage in negative direction, right? So 0 to minus 75 microvolt, we will have a linear relationship between difference input and output. But once we go beyond this 75 microvolt, my output is going to saturate like this. Okay, so this will be the practical voltage transfer curve, right? Then this range AB is the input range for linear operation, which is very small. Okay, it is in terms of microvolt, you can see. Okay, so now if I talk about Vd, if Vd is greater than corresponding to B, the output attains positive saturation level. Okay, if Vd is less than corresponding to A, the output attains minus V saturation. Okay, so this range AB, you can say, we can conclude that range AB is input range for which my output varies linearly with the input. Okay, but as we know, the open loop gain is very high. Okay, and this is the reason why the range practically the range will be very small. Okay, in this case the range you can see is plus or minus 75 microvolt. Okay, so during this range only we will get the linear relationship between input and output voltage. After that our output voltage will saturate between negative and positive saturation value. Okay, so this is the voltage transfer curve in case of ideal op-amp and in case of practical op-amp. Okay, so we have talked about the ideality of the operational amplifier, but all these values, whatever characteristics we have seen, is having the ideal value. Okay, and practically this is not going to happen. Okay, whenever we actually use the operational amplifier in our analog electronic circuits, at that time we will be limited with value. Okay, so we will have some practical values of all these characteristics. Okay, so whenever we are dealing with the practical operational amplifier, how this op-amp will behave, what will be the input voltage range, what will be the output voltage, what will be the value of the bandwidth, what will be the value of gain. Okay, all this thing matters. Okay, and this is the reason why you need to understand the equivalent circuit of practical op-amp. Okay, so this circuit will represent operational amplifier parameter in terms of physical components. For the purpose of analysis, we call it equivalent circuit. Okay, so we will see the equivalent circuit of practical operational amplifier, and then we will try to understand the practical characteristics of this operational amplifier. Okay, and then whatever other important parameters which are associated with operational amplifiers are there, we are going to study these parameters one by one. Okay, so we will stop here. In the next lecture we will continue with the equivalent circuits of practical op-amp, and we will move on to the op-amp characteristics, practical op-amp characteristics then. So if you have any questions, then you can ask. Yes, please. Anyone having any questions?